All right, so now we're going to get into some of the basic programming structures we have in R. And remember that perhaps at the beginning of the course, I told you the SAS component of the course would be more business related, and now R is going to be more academic focused, and its application even within industry is more computational in nature than perhaps other statistical programming languages are. So we're going to go ahead and jump right into how we use the programming structures and basic programming types in R to do things like simulations and generate data. So here's the basic idea of a simulation. This is where you're just trying to generate some sort of random data, whether you're testing a procedure or testing a methodology. It goes like this. We initialize a simulation. We maybe declare some parameters for a model, a set number of runs. Then we generate data. So maybe the data generated is 1,000 binomial random variables. Then we fit whatever we're doing on that data. We treat the data as if it is simply observed data. We store our results, and then we repeat that often 1,000 times, 10,000 times, or even more. Finally, once we're done with all those iterations of the random data, we go and we summarize all of those results and output our final results. Right now, it's not so important you understand that whole process, but that's just to give it a framework that we'll reflect upon later. What's nice is R has many functions for random generation of data. It can be very specific or be very general. For example, the sample function will just provide random samples with or without replacement for any kind of data that you already have. We're going to be talking about other types of processes later, but this may even fit better into a second programming course. This is the most basic way that we can start generating data. For example, if we have a data set X and we want to create a resample or a sample of that data, we can specify the size. And then whether or not we sample with or without replacement. So replace equal true means we sample with replacement. Replace equal false means not. And we can also specify a weight vector. The sample size function is just going to give you that sample size from a vector X. Those probabilities can weight different observations of different amount. If replace equals false, the probabilities are going to be updated after each sample is drawn. So for example, here we would get, because replace will be false by default, here we could not get 5 and then 5 and then a 3, because once 5 is selected in the first random sample, it is no longer in the pool. We would just have 1 through 4 available. But when we add replace equal true, we can even take a larger sample size than the population and get multiple of the same observations. And we can also specify weights associated with each of those 5 possible outcomes, 1 through 5. So notice that's 1, 2, 3, 4, 5, where we're more heavily weighting ones. And we can see that in the result. We can generate specific statistical distributions very easily. Generally, if we're going to randomly generate this data, we start with a prefix of R for random. And here's a list of the most often used ones. There are some individual ones coded also within R. I have one coded, in fact, within R. And but these are the ones most often used. This might be useful for you to print out, in fact. The parameterization can sometimes cause some confusion to students. I know that comes up most often with the gamma distribution I've seen. So pay attention to that. Here's some examples. Let's focus on something familiar and easy for all of us, the standard normal distribution. So notice, first of all, we have our mean at 0 and our standard deviation at 1 for all of these. If we didn't specify that, that would have been the default assumption of any of these function calls. So D stands for density. So this gives us the density after a particular point in the distribution. Okay, P stands for probability, and specifically probability distribution function. So here this gives us the area to the left of 1.96. Notice how we know the area to the right of 1.96 is 0.025, and so the area to the left would have to be by consequence of the area being 1 under the entire curve of 0.975. We can specify the lower tail is false, and we get the upper tail, by the way. Q stands for quantile. So what gives us that quantile where 2.5% is to the right and 97.5% is to the left? Well, it's 1.96, and here we can retrieve that automatically if we did not know it. Finally, R stands for random generator, and here we get 5 randomly generated standard normal points, and these are all consistent with the standard normal distribution. Here's a few of the statistical distributions you can get. You can get this all from documentation in R. We want to be able to create simulations that are repeatable. This will be your second homework assignment. Will really emphasize this, and you'll actually be writing a repeatable simulation in your second homework assignment. For a simulation to be repeatable, we need to specify the type of random number generator and then that initial state of the random number generator. I have never worried about what kind of random number generator I use with an R. I always just go with the default, but if you want to know more about that, you can run the RNG_kind function. The simplest way to set your initial value is to use the set.seed function, and this will provide by you a seed. You can choose this from a random number table or just write down, make a note to yourself what that seed is and keep it in your code. Different seeds will give you different pseudo-random values from the algorithm used for random generation of numbers within R. And calling set.seed with the same seed number, so that same number in there for seed will produce your same results. So you can repeat your simulation. So if somebody says, I don't believe you got that result, if you've set your seed, you can recreate and show them how you got a particular result exactly. If the seed is not specified, then your random number generator is initialized using the time of day, so you would never be able to repeat your exact results. So I always set my seed whenever I run simulations. I don't go to the trouble to look up my number in a random generator table, but I just pick a random number by some other mechanism. So here's some repeatable simulations. Here the set seed, here's just a number. Okay, this number is not so important as much as you just need to remember what it is and keep that in your code. Okay, here we get some uniform and normal random variables. If we set a new seed, we get a distinct set. If we go back to our original seed, we get those same sets that were above and so forth. Okay, so now a little bit about control structures. This, again, should be somewhat familiar to us if you've ever worked with any other programming languages. In general, though, the syntax is pretty self-explanatory within R. The if-else control structure is going to determine when expressions run depending on whether some condition is true, and the condition goes within these parentheses. If-else is very similar, except it's going to provide an automated version of this that works in a slightly different fashion. We'll talk about why at times we use the if-else sequence and sometimes we use the if-else command. Switch will evaluate different expressions given a particular value observed in the data. So this is really useful when you're creating categories based upon certain types of outcomes. A for loop is going to iterate through a sequence over a index. So you might have I equal 1 up to 1,000. Your for loop would iterate through a fixed number of those iterations. A while loop is going to continue the programming statements within that loop until a certain condition is deemed false. Repeat is just going to repeat. A little bit dangerous. You need to make sure you include a break statement in there somewhere. break will break out of any loop. You can actually use it in any of these kinds of expressions, including the if else. Finally, next, we'll just go to the next iteration of your loop. So if you have an error occur in your code that is not a fatal error but needs to be recorded and then moved on from, you can use the next to process to the next iteration in your control sequence. Okay, so we're going to go into more detail here. Let's take a little break first and come back to this.